What's up, Internet? Addison here with Addison Academy, and we're going to dive into a fun physics problem today. Not only the solution, but also the problem-solving process that got us there. I hope you enjoy and learn something fun. Here we go. So I saw this interesting physics problem yesterday, and it was giving us a little bit of fits. So I thought I'd just dive into it and share the solution with the Internet. So we've got a classic Pulley system going on here, and we are told what one of the forces is. There's some friction force with that top block sliding on that surface there, and it's asking what the tension in the rope is. Always useful to get clear on the question before you try to solve it. It's kind of like trying to find the goal before you shoot the ball, right? So what is the force of the tension? I'm going to go ahead and set myself up for success by putting that on the bottom of my paper. All right. So free body diagrams, what are they? They are diagrams of all the forces at play. All of the forces are going to determine which direction this system is moving in. In other words, whether it's accelerating or not and in what direction. So at first, it might be easy to think that this system is not accelerating because we don't see it moving. But that would be a mistake because nowhere in the problem does it tell us that the system is not accelerating. And as we're going to find out in a second, the system is accelerating. All right, so let's draw all the forces that are acting on the system. So what's acting on this large block? Well, gravity is usually acting on things, and it's acting on this block here. And of course, the block is not accelerating, right? Let's just go ahead and put our most helpful equation on our piece of paper. F ma, or F equals ma, right? And so what that means is if the acceleration is 0, then the force will be 0. If the force 0, and by the way, it's not just the force, it's the net force. Let's be a little more specific. If the net force is 0, then the acceleration will be 0. You can't be accelerating without a force. And if you're not accelerating, then you can't have a net force. So my point here with this block is that it's obviously not going through the table or whatever this surface is, and it's not levitating. So therefore, the F net in the vertical direction is 0. And that's, of course, because the normal force is canceling out the gravitational force, right? So we also tend to break forces down, and I don't see this being explained well enough on the Internet, so here I am this morning. We tend to break forces down into their y component, their vertical component, and their x component, their horizontal component. And that helps us make sense of two dimensions more easily by considering them one at a time. And that's why, for example, when we have diagonal forces, we tend to split them into their x component, their horizontal component, and their y component, their vertical component. Anyway, as we can see, there are two vertical forces acting on this 10 kilogram block, but they cancel each other out. And for that reason, we really don't have to think about them again. Then what else is pulling on this block? Well, the force of the tension of the rope is pulling on the block to the right. Okay? We don't yet know whether the force of the tension on the rope is greater than the force of the friction. If it was, then the block would have acceleration to the right. If it wasn't, well, if the force of friction was somehow greater than the force of tension, the block would be being pulled to the left. Of course, that doesn't make sense because friction doesn't move things. So the force of the tension is probably at least 15 newtons or more. Otherwise, we'd be in a world where the friction can move things of its own accord, which is not the case. Okay. Then, what's happening here? Well, the tension is pulling up on this 2 kilogram block, right? It's not in free fall. It's being stopped by the tension of the rope. And then there's a force of gravity pulling down on this 2 kilogram block. So those are all the forces. There are 6 forces at play. We can go ahead and ignore the force of gravity and the normal force on that block because they cancel each other out. And what we're really interested in is the net force. Okay. Now, one thing that makes this confusing is that we have a pulley here, and that pulley is changing the angle of the rope by 90 degrees. So if somebody pulls down on this rope, then it pulls this rope to the right. And so what's somewhat diabolical about this problem is that we're so used to splitting forces in terms of their x component, their horizontal component, and their y component, their vertical component. But meanwhile, this pulley is taking these vertical forces and turning them into horizontal forces on this block. Does that make sense, right? pulling down on this rope pulls this rope to the right. Therefore, a downward force on this rope is the same thing as a force to the right on this rope. Okay. Another key insight here is that these blocks are connected together by the same rope. So this tension force is indeed the same as this tension force. And since this tension force is pulling up and this tension force is pulling to the right, these two tension forces offset each other. All right? We talked about how pulling down is the same thing as pulling to the right. So pulling up is the same thing as pulling to the left. So for that reason, this tension force pulling up and this tension force pulling to the right are actually going in the opposite direction. Even though they're at a 90-degree angle to each other, this pulley makes them opposite. So these tension forces are going to cancel. So another insight, these blocks here are tied together. So they will be accelerating at the same speed. Now, if they're accelerating at the same speed, we can refer to them as a system. This is very much the same thing as that the four wheels of your car and your windshield, they're going to be accelerating at the same speed, right? So, or an even better example might be the seats in your car and the roof of your car. Wheels are a little more complicated, but same idea. They are accelerating at the same speed. Therefore, you don't have to calculate them separately. You want to consider that car as one system. It's probably the easiest way of dealing with it. So these two blocks can be considered one system. So we're going to evaluate this as a complete system. And we're going to be interested in calculating what the F net of the system is. Now I'm going to go ahead and solve F equals ma by dividing both sides by m. Why do I want to do that? Well, that isolates acceleration. The m's cancel out, so I get the F net divided by the mass is equal to the acceleration of the system. In order to figure out what the tension in the rope is, first I'm going to have to figure out what the acceleration of the system is. And it turns out in this situation, the acceleration is non-zero. All right, now, we know that these tensions are going to cancel each other out in terms of finding the net force. Okay, so for the moment, we're going to disregard those. So what are the only forces acting? Well, we got the force of friction we're given to in the problem is 15 newtons. And we have the force of gravity pulling down this 2 kilogram block. Well, we better figure out what that is. F equals ma. That's our guiding light in these problems. The mass is 2 kilograms. The acceleration of gravity is 9.8. Multiply 2 times 9.8, you get 19.6. So the force of gravity pulling down here is 19.6 newtons. Okay, so what's the F net? Well, we're pulling down with a strength of 19.6. And we're being impeded by this friction force, which is pulling to the left. Now, normally we don't mix left forces with down forces, but we've already discussed how this pulley system is combining these vertical forces with these horizontal forces. So the friction is pulling 15 degrees against the gravity. So we're going to subtract 15 to find the F net. Okay. Now, the mass of the system is the mass of the entire system. So we have to add the 10 kilograms with the 2 kilograms to find the mass of the system. Okay? Add all the components. For example, if you want to find the mass of a car, you got to add up all the parts of the car if you're not given the mass. All right, so do some quick calculations here. 19.6 minus 15 is 4.6, and 4.6 divided by 12 is 0.383 repeating. So we'll leave it here at 0.38. It's going to be equal to meters per second squared. It's going to be equal to our acceleration. Okay, so now we know what our acceleration is. And it's quite clear from this initial analysis, right, that the acceleration is non-zero. The system is moving. The system is sliding this block to the right. And the system is moving this block, gravity is pulling this block downward greater than this tension force is resisting. So notice that we found the acceleration without knowing the tension. That might strike you as a bit of a surprise. How did we not know all the forces in order to find the acceleration? Because the tensions canceled each other out in the system. So now we're going to look at one of these blocks individually. Okay, so let's clear up some space for us to do that. Now, why are you allowed to do that? Well, because these blocks exist as a system, do they not? But they also exist as individual blocks. Isn't that true? So we can view them in both regards. And we have to be careful, right? The value of analyzing them as a system is that the tension force is canceled out. If we view them as individual blocks, the tension forces will not cancel out. So let's take a look at the small block, okay? The 2 kilogram block. What are the forces acting on the 2 kilogram block? We have the tension pulling up, and we have the force of gravity pulling down. So let's run an F net is equal to M times A analysis. Well, what would the forces be on the block? We just mentioned what they are. Gravity is pulling down, and it's being mitigated minus the force of the tension in the rope, which we still don't know what it is. But the good news is, now we know the rest of the variables in the F equals ma equation. It's equal to the 2 kilograms times my acceleration, 0.38. Wonderful. So if I go ahead and run the math there, right, add the force of tension to both sides to solve for it, subtract by 2 times 0.38, which we should do. 2 times 0.38 is 0.76. So we end up with 19.6 minus 0.76 is equal to the force of the tension. 19.6 minus 0.76 is, of course, 18.84. So the force of the tension is 18.84 newtons. So let's take a step back there. How did we get there? Okay. First of all, we drew a force body diagram considering all of the forces at play. Then we realized what's happening with this pulley. It's distorting the forces by 90 degrees. So the vertical forces on the 2 kilogram block are the same thing as the horizontal forces on the big block. That's not immediately intuitive. That takes a second of processing to get there. Then we realized that the tension forces are the same because it's the same rope. A rope can't have two different amounts of tension in it just because it goes through a pulley. It has the same amount of tension. That enables us to cross out the tension forces when evaluating the two blocks as a system. What does that allow us to do? That allows us to use the gravity force and the friction force to calculate the acceleration of the system. Now, the acceleration of the system is transferable to the acceleration of the individual blocks because the blocks are, of course, accelerating at the same speed as the system because they're part of the system. So then we're able to look at one of the blocks, like the small block, use the acceleration that we calculated from the system, no longer ignore the force of tension because in one block, the force of tension is not canceling out, and that enables us to find the force of the tension. Now, you might be asking, so here's a bonus, you might be asking, well, why'd you pick the 2 kilogram block? Why'd you pick the vertical tension force? What about the horizontal tension force? Well, let's do that for fun. Because you could have analyzed the 10 kilogram block and you would have discovered that it is subject to Newton's second law of motion as well. The acceleration is a function of the force and the mass, Newton's second law, right? And so what's happening here? Well, this tension force is going to be pulling it because we know that the block is accelerating that way. So the F net is the tension force minus the friction force, which is 15, is equal to the mass, 10, times the acceleration, which we've already calculated to be 0.38. Run some math on that. The force of tension, we could do this math in our head, is equal to 10 times 0.38, which is 3.8 plus 15. Wait a second, look at this. The force of tension equal to 18.8 newtons. And so now by double confirming that we get the same force of tension, whether we analyze the big block or the small block, after considering this in a system, we should be quite confident that we have the right force of tension in the rope. I hope this was fun. I wanted to sort of share not only how to do this, but a little bit of the behind-the-scenes problem solving that enables us to get to the right answer. Not just what the right answer is, but how do you figure it out? You think it through. Start with the forces. consider what you know to be true, what facts you know to be true, and then use some creativity to put those facts together with the fundamental laws of physics in order to figure out truths about the universe, like what the heck is happening here with these two blocks, a little bit of friction and a pulley. All right. Hope this was fun. See you later.